Well, hello physics folks, and welcome once again to Doc Onco's Physics. Keith Onco here. Today what we want to do is look at yet another one of Newton's problems, and this one's going to be a block on a ramp that does have friction, and it's connected by a cable to another block over a pulley. So this may seem complicated, but it's really just a matter of applying Newton's laws to each one of the blocks. And also, one of the things I tried to describe in the last problem with an object on a ramp is that we get to define our own coordinate systems for each one of the objects that we're dealing with. Okay, so let's look at that first. Let's use green here. The coordinate system that I'm going to use for this object over here, well, this object I can just use a standard coordinate system, right? Y and X. Right? And that's going to work well because gravity is working in the strictly y direction there. But our block is going to be going down this ramp here at some angle, and in fact that angle is going to be once again 30 degrees, and it's going to be traveling in the direction of the ramp itself. So what's the coordinate system I'm going to draw? I'm going to create a coordinate system like this, right? Where x is in the direction of the ramp and y is perpendicular to the ramp itself. Perfectly valid, okay? The only things we need to make sure that we do is when we write equations, and I'm going to call this block number 1, this one number 2. When I write equations for block number 1, I've got to only use data from this coordinate system and either the x direction, if that's the equation I'm writing, or the y direction, if that's the equation I'm writing. And for block number 2, same thing. I got to use this coordinate system. And in fact, for block number 2, it's really only going to be y direction information. Okay. So let's see what we've got for block number 2. That seems to be the easiest one to look at first. I've got a rope attached to block number 2. Right? My rope is always going to be pulling, and so I'm going to have some tension in that rope going in the upward direction. What other forces do I have on block number 2? Well, I've always got gravity, right? And so gravity is going to be pulling in this direction, and so that's going to be the force due to gravity on block number 2, and that's going to be m2 times g. Okay, so I've got that. Okay. As far as masses of our blocks, I'm going to say that, let's see, put this in orange. Let's say that this one's going to be 4 kilograms for block number 1. And block number 2, even though it looks smaller, we're going to give this one 20 kilograms. It's going to be a much more massive block. Okay. All right. So let's look at, so we have our forces for block 2. That was easy. Tension pulling up, gravity pulling down. Now let's look at the forces for block number 1. Well, we've got gravity, all right? And gravity, remember, always goes in the direction of the center of the Earth. Okay, well, this is the direction of the center of the Earth. Is that going to help us? Is that in either the x direction or the y direction for our coordinate system up here? No, it isn't. So what I'm going to have to do is I'm going to have to determine my x coordinates and my y coordinates. All right, so this is a right triangle here. This is going to be my x coordinate of gravity. All right, this will be my y coordinate of gravity right there. Okay, and just to throw a little one more problem in the works here, we're going to say that we have a coefficient of friction, kinetic friction, between the block and the ramp equal to, say, 0.2. Okay, so we're going to have that as well. So we're going to have a lot of things going on. Let's first figure out the forces that are on the block that's on the ramp. Well, we have a cable connected to that block. Cables only pull, so that's going to be the direction of the force due to the cable. We're going to have our force due to gravity in the x direction, all right, pulling down, all right, and that's going to have some value. we're going to have our force due to gravity, all right, and that's that right there, all right, and that's this component right here. And we're also going to have our normal force, all right, our normal force on our block, all right. And we're going to have to figure all those things out. We're going to have to come up with some numbers. But before we do that, let's actually write the equations that we have, all right, and then we can actually plug numbers in. That might be a little bit easier. All right. We don't have to plug numbers in right away. We can write the equations and then plug the numbers in. So let's write the equation. Let's go over here. For block number 2 in the y direction, right? It has the least amount of things involved in it, so it's the easiest one to write. So what do we got? We have tension pulling up, right? And we have gravity pulling down. So it's going to be tension minus, right, and gravity is equal to m2 times g, so 20 kilograms times 9.8 meters per second squared. Oh, I left the meters per second squared off. So forgive me, please, for that. It's going to equal the mass of block 2, which is 20 kilograms, times the acceleration of block 2. Okay, now, which way is block 2 going to be moving? Will it be moving up or will it be moving down? Well, common sense in this case tells us that it's going to be moving down because it is much more massive than block 1. All right, and it has the full force of gravity acting on it. All right, and so since we're assuming it's going to be going in the downward direction, I've got to put a negative in front of A2 here, all right, because it's going to be moving in the downward direction. It's going to be accelerating in that direction. All right, so this is my equation for block M2. And so when I do the calculations and come up with some numbers here, let's see what we've got. I've got T minus 196 newtons is equal to 20 kilograms times A2. All right, and we're going to be able to get rid of that subscript with the 2 next to the A because our acceleration, again, is going to be the same for each block. All right. Even though they're going in different directions, the acceleration is the same because they're connected by this perfect cable. All right. Now let's look at the equations for block M1. All right. Well, we have a normal force and we have a force due to gravity in the y direction. Is our block accelerating in the y direction at all? All right. Our y direction being this coordinate system here? No, it isn't, right? And so our normal force for block 1 minus our force due to gravity for block 1 is going to equal 0. So our normal force is simply going to equal, right, Fyg. And that is going to be, right, since this is our incline is 30 degrees, it's going to equal, well, Fg, all right, for block 1 is going to be 4 kilograms times 9.8 meters per second squared. All right, that's the force of gravity on the block itself, but we need the force in the y direction. Okay, so that's going to be times the cosine of 30 degrees, which happens to be 0.866. After you do these things for a while, you begin to remember what the cosines and sines of different angles are. All right, and when we do this math, our normal force is going to be, let's see, 4 times 9.8 times 0.866 is 33.94. We'll round it up to 34 newtons. Okay, so this is our normal force on block 1. Okay. All right, well, what do we need that normal force for? Well, we said there's friction. Okay, so we need to know what the frictional force is, all right, on our block. And oh, by the way, what did I forget to do? I mentioned that we have a coefficient of friction, but I did not draw in our force due to friction. I apologize for that. All right, so we have our force due to friction also pulling in the opposite direction of the motion. The motion is going to go to the left, so friction will be going to the right. So what's our force due to friction going to be? Well, it's going to be mu, which is 0.2, times our normal force, which is 34 newtons. All right, and when we do that math, let's see here, we get 34 times 0.2, and that is 6.8 newtons. All right, so the force due to friction is going to be 6.8 newtons. Well, we know our force due to friction. All right, we have that. It would be very helpful to have Fxg, all right, the x component due to gravity here. What's that going to equal? Well, again, it's going to equal 4 kilograms times 9.8 meters per second squared times, this time we're looking for the opposite side, so it's going to be the sine of 30 degrees, which is 0.5, all right? And we do that math, I get 2 times 9.8, that's 19.6 newtons, okay? So that is our x component of gravity pulling down the ramp, all right? So do we have all of our forces in the x direction now? Yes, we do, all right, for block number 1. So now we can write our equation in the x direction for block 1. What do we got? Well, we have tension pulling to the left, so that's going to be a negative t, okay? And we have these other forces pulling to the right, all right? We have our force due to friction, which is 6.8 newtons, plus 19.6 newtons, all right? And that's going to equal the acceleration of the block, which is going to be going to the left, right? So it's going to be negative a times 4 kilograms. I'm going to run out of space here. So 4 kilograms times negative a, whoops, it's a bad looking a. That's a, say A1 there, okay? I'll rewrite that down below. All right, so let's collect all this stuff together. And when we do, I've got the sum of the forces in the x direction is equal to negative t, all right? And 6.8 plus 19.6 happens to be 26.4. And that equals negative 4 kilograms times A1. All right. Now remember, these are connected by a perfect string, and so we can get rid of our subscript. So I'm going to get rid of that subscript over there, and then way over here, I'm also getting rid of the subscript over there for equation number 1. So I'm going to circle my equations in red because this is getting a little bit hairy here. So there's one equation, and here's our other equation. So what can we do with these guys? Well, we have a t minus 196 newtons equals 20 times a, and we have a minus t plus 26.4 newtons equals minus 4 kilograms times a. So I'm going to put those up at the top here. So t minus 196, and I'm going to leave the units off for now just because I'm running out of room, equals 20 times a, and I've got a minus t, all right, plus 26.4 newtons is equal to minus 4 times a. Well, nicely enough, if I just add these two equations together, because I've got a t and a minus t, what I end up with is negative 169.6 is equal to, let's see, we have 16a here, okay? And if I divide each side by 16, I get a value for a of negative 10.6 meters per second squared. Why is it negative? Because it's either going to the left or it's going down, all right? And so our acceleration is going to be negative in this case. All right, so that was a reasonably complicated problem because not only do we have two objects, but one of the objects was going down the ramp, so it's at an angle. We have to take our coordinate system and convert it. But if you follow the steps, right, you should be able to do these problems. Hope that helps, and have a great day.